So the next speaker is going to be Lingyuan Ye, and the title of the talk is The Pro-étale Site for First Order Logic. Lingyuan, the stage is yours.
Thanks, Ivan. Thanks for having me. Thanks for everyone's here. It's my first time attending Ithaca, and I'm sort of ashamed that this is my first time appearing here. But okay, through this, I would love to participate more. Um, and thanks for the invitation. So today, I'm going to tell you a bit about the, the kind of a story for first order logic. So I will assume basic knowledge about kind of traditional categorical logic. But if you're not familiar with anything, I'm happy to be interrupted. Um, yeah, at any time. But okay. So the story kind of begins from a very traditional approach of looking at logic, which is if we have a theory, now for us categorical logicians, by this I mean possibly a pretopos, say, a first order theory, we study this theory by looking at its models, right? So today I will use the notation, this weird notation for this to denote its category of set models, right? So the category of models are just the category of coherent functors from C to set. Okay, and you'll see why I use this notation later on. So, like Gödel first proved this completeness result, although, of course, Gödel didn't write it this form, but for now we know it's of this form. So we can look at actually the kind of a sort of illegal preshift category from the category of all models to set again. And our original syntax, so our starting theory, has an evaluation functor mapping into this preshift category. Basically, it sends a formula phi to the functor that takes any model and just evaluates that model at phi and return the set, right? So this is the evaluation functor. And completeness kind of just means this evaluation functor is faithful, right? Or conservative equivalently. So it means that if I have two different things in my syntax, possibly or necessarily I can find some model here that distinguish them by evaluating them, right? So this is the, if you want, this is one of the categorical way of formulating this completeness results, which is that models can separate syntax. And it happens that this evaluation functor is itself a coherent functor. So it preserves actually the coherent structure in C. And this embedding, this kind of evaluation embedding does not only work for say, pretopos, which is first order logic, right? It works for a lot of fragments. Say it works for lex categories, regular categories, lextensive categories by considering appropriate notion of models. Okay. So this is kind of the completeness result. So let us, the categorical logicians kind of takes this result a step further, which is now usually called this conceptual completeness. So completeness means separation of syntax by models. Conceptual completeness asks for a reconstruction of syntax, right? From the category of models, can we actually reconstruct our syntax? And so for the easy case, let's see just be a small left exact category. So this is the essentially algebraic logic, if you want. And it's, of course, its corresponding category of models is just the category of lex functors from C to set. And again, we have this evaluation functor from C to this preshift category. So the usual Gabriel-Ulmer duality says that, well, this embedding is actually fully faithful, and we can characterize its essential image as those presheaves that preserves all limits. So it's a right adjoint, so preserves all limits from this category to set, and also all future colimits, right? So this is a very clean result that not only says this is fully faithful, but okay, we can actually characterize the syntax coming from C as certain special presheaves into in the codomain. Okay, this is kind of the easy case for lex categories. For pre-topos, so if we return to the first order case, we can still characterize the subcategory C in this pre-sheaf category, but now things get slightly more complicated. So Mackay have this celebrated conceptual completeness result, which says that, well, the essential image of C actually can correspond to functors, preserve the so-called ultra products on the category of models. And also notice that C into the evaluation embedding is not full, so you also have to characterize the morphisms in C. Those are kind of functors that respects this preservation of ultra products. And then later on, Lurie kind of factorized this evaluation embedding into the sheaf topos. So this sheaf topos is the usual coherent topos over C, and we can embed fully faithfully along UNETA. We also have an evaluation functor from the of sheaves given by any model. And this Lurie characterized the essential image of the sheaf as certain Lex functor for ultra products. So Lurie called this left ultra functors. And this is kind of the state of the, this is the reconstruction of syntax through the category of models for first order theories. But part of the difficulty, if you compare to this Gabriel-Ulmer duality, is that actually these ultra products are not characterized by universal property on the category of models alone, right? So the ultra products are certain co-limits of limits, but the corresponding limits doesn't exist in the category of models. Just the ultra products exist in the category of models. So it's not directly defined by universal property. So recently, there's a lot of approach on this, how to characterize or how to encode this data of ultra categories as certain algebraic data. So this is basically the approach by Mackay, by Lurie, and recently there are a lot of other works on this that specify these ultra products as additional structures in the category of models. And usually it's a large amount of data. So you have to specify for each ultra filter on each set, how to compute the ultra products, and so on and so forth. So this is kind of the algebraic approach. So there's also kind of a quite different perspective. Like Ivan in 2022 had this approach that understanding the ultra products of in the category of models for coherent theory via certain can extension property in the two category of topoi. The nice thing about this is that it recovers the description of ultra products again by a universal property. So it's not a structure anymore. It's properties. And later on, so Ivan and I have kind of similar characterizations for other subfragments of geometric logic. And actually, in this framework, we have a new conceptual completeness proof on the way. I hope this is joint work with Ivan de Liberty and Umberto Tarantino. I hope they're both here. I hope my co-authors are fine with me announcing this here. It will be out soon. But today I'm presenting a kind of yet different approach for both of these two approaches. And this is inspired by work in algebraic geometry, where this recent work on condensed approach to algebraic geometry and this so-called exodromy theorem. Okay, so let me go into this. The idea is that we want to put the syntax and the semantics kind of into the same place. And the approach of this is that we can like embed both of them into the pro-completion of the syntactic category C. So on one hand, you can identify the pro-completion as the formal completion of C by co-filtered limits. So, and this is the canonical embedding into that. But on the other hand, you have an equivalence between the pro-completion with the opposite category of Lex functors from C to Z. And of course, the coherent models are coherent functors are Lex. So the opposite category of models embeds into that. So kind of you have a natural habitat that bridges both the syntax and the semantics. And just so you know, the equivalence takes a pro object f in here as a lex functor. It takes its value at phi in C is given by the co-representable, right? So this is how this equivalence is. Just, I'm sure you're familiar with this. On the syntactic side, this embedding is kind of well understood because it's a free completion of co-future limits, and the objects in C are exactly the co-presentable ones, right? Namely that those the representable functor on those takes co-future limits to future co-limits. And the nice thing is that if C has certain, say, additional categorical structure, say if C is regular or C is lextensive, then so is this pro category. Okay, and this is kind of our primary investigation today. So actually, we would like to understand this side a bit better, right? So we can also embed the models into the lex models, so to speak. But what are kind of the difference between them, and how can we characterize, say, this part of the models inside the pro completion? And so that if we understand both sides appropriately, maybe then we can find additional information on the relationship between C and its category of models. So this is kind of the idea of this pro business. Before I present kind of the work on this side, I just want to mention that maybe you would ask me why we're considering this pro completion in the first place. So in algebraic geometry, they kind of consider this pro completion because they have some observation on cohomology of certain on the étale cohomology of schemes, and they realize that the L-adic étale cohomology are best described by certain profinite limits or co-future limits of individual cohomology, and this is the Peter Schultz work that leads to considering this pro completion. And so this is like considering this is fully inspired by that. And this is actually used in Lurie's approach to prove conceptual completeness of Mackay's results, right? So this is completely borrowed. But hopefully after today, you will see that from a pure logical perspective, taking the pro completion is also very nice construction. And I will tell you the reason is because we can fully characterize the difference between the lex models and the models. And the slogan is kind of that the lex models are exactly models up to a profinite set. Okay, I will explain this in a bit, starting from now. So this works for pre-toposes and so on and so forth. But okay, for simplicity for today, I will let C to be a lextensive category. So a lextensive category is just a lex category with disjoint and universal finite coproducts. Right? So it doesn't have the image factorization as a regular category, so this makes things slightly easier. But okay, essentially everything will work for pre-topos as well. And in this case, of course, we're considering the difference between lex functors or lex models and lextensive models, which are left exact functors, which also preserves finite coproducts. So we want to understand when a lex functor preserves finite coproducts for lextensive categories. But in this case, the answer is very easy, right? So if you have two lextensive categories C and D, and you have a lex functor between them, this functor preserves finite coproducts as long as it preserves the single finite coproduct 2, which is 1 plus 1. And the proof is very simple. So suppose you have two objects, and you want to say, well, F preserves this coproduct. You form this pullback in C, and because F is left exact, it preserves these pullbacks. And if F preserves 2, then the bottom row will be a coproduct diagram in the codomain category D. And by D being lextensive, you actually infer that, well, F applied to phi plus psi must be the coproduct of F phi plus F psi. So this is a very simple proof. And let you know, right, the lextensive structure makes preserving coproducts really easy, which is everything is controlled by 2. And sort of from this, you kind of could guess that why there is profinite sets happening in the story, because 2 is a Boolean algebra. So what we do is that we want to kind of formally measure the failure of a Lex functor preserving finite coproducts, right? By the previous results, we can just look at its value at 2. So we can build this functor. So from the pro-completion of C, we can build a functor from this to the opposite of Boolean algebras by evaluating at 2, right? If you understand from the previous equivalence from C, the pro-completion of C with left exact functors, looking at the representable functor at 2 is by evaluating a left exact functor at 2. So this measures how much difference a Lex functor preserves 2. Okay, so it gives certain Boolean algebra, and then we take its Stone duality to give a profinite set. Right, so this is how this functor is constructed. This is my functor pi, and you may think this as maybe the underlying connected components, the underlying shape of a left exact category or of a pro object. Right. So in particular, the previous result says that F preserves, so given a pro object or left exact functor, it preserves finite coproducts, or it is a left lextensive model if and only if the pi of F is a singleton set, right? Because the singleton set is the dual of the Boolean algebra 2, and if F preserves 2, then the pi of that will be the singleton set. So this is kind of, this pi measures the failure of a Lex functor preserving finite coproducts by assigning it a profinite set. And just so you know that pi is actually part of a left of an adjunction where there's also a kind of a right adjoint of taking the constant profinite set into this. Okay, but anyway, this is a setup. But actually we can go further. So this pi of F actually has a universal property, which is that you can factor a Lex functor as follows. So here, pi of F is a profinite set. So it's a topologic space, and you can take the sheaf topos of the topological space. And what I claim is that the Lex functor actually factorizes as a lextensive functor. So now this F hat preserves finite coproducts in C, followed by the global section of this sheaf topos, right? So this is sort of the slogan that a left exact functor, a Lex functor, is kind of a lextensive model, or is a model up to a profinite set. So up to the global section of a profinite set. So this is kind of the sort of a universal property of this, the profinite shape, or the connected components of a Lex model. And how you build this lifting is very easy, because pi of F is the Stone dual of the order maps from F to 2. And because, as I mentioned, the pro completion will be lextensive as well. So this basically just encodes all the decidable subobjects of F inside the pro completion of C. And so for any clopin in the profinite set, you just take its value at that decidable subobjects. And this is how you lift F to the F hat here, okay? But okay, the proof is not important. This idea, I think, is quite interesting. But so now, this means that we actually want to look at not just lextensive functors from C to Z, but actually from lextensive functors from C into a sheaf topos over a profinite set. Right, so we can actually kind of contemplate on this pseudo functor, right? So this will be the category of a profinite set, and we have a pseudo functor that takes any profinite set to the category of lextensive functors from C to that sheaf topos, right? So its value at S will be the sheaf valued models of C over S. Okay, this is a pseudo functor. And we can also take the formal opposite of the pseudo functor, because if you notice before, the embedding from the model side is by embedding the opposite category of the category of models. So we are also kind of taking the formal opposite of this pseudo functor, basically by taking the opposite of each fiber. And then we can take the Grothendieck fibration and of these pseudo functors and get two fibrations over the profinite set, right? So this will be kind of the opposite of profinite models. This will be the pseudo functor of profinite models. And interestingly, so the total category, so if you look at the total category of this Grothendieck fibration, it's sort of is reminiscent in the construction of, say, the good old ring space construction, right? So its objects are pairs. So for a profinite set, together with a model of C over that profinite set, and the morphism between them is a continuous map that, also together with a map of models between the pullback of OT into OS. So this is usually how you construct the category ring spaces or something, right? Okay. Anyway, but here's the kind of killer theorem. The killer theorem says that previously, if you recall, that we have a lifting operation, taking every lex functor, maybe now seen as a pro object, into a lextensive model over a profinite set, so into something here. What I'm claiming is that this lifting operator actually gives you an equivalence between the pro-completion of C over profinite set and this Grothendieck fibration over profinite set. And this equivalence is over the profinite set, right? So this is an equivalence of Grothendieck fibrations, or if you like, of pseudo functors. So this is kind of the killer theorem that brings out everything I will go into say later. Okay, and this equivalence actually gives us a formal way of recovering the conceptual completeness theorem that I speak about at the beginning of the talk. But before that, I want to connect to you how this theorem kind of interplays with works. And so I just want to kind of take a detour that tells you how this equivalence is basically a generalization, or actually stronger results of Dier's work on multi-representable categories. So Dier's work basically is like this. So if you have a lextensive category, of course, his work is much more general than this, but okay, say C is a lextensive categories, then the inclusion of the lextensive models into the lex models have a sort of left multi-adjoint. So it doesn't have a reflection, so it doesn't have a left adjoint. But for every lex model here, you can have a family. You can map into a family of lextensive models. So for each of Fi, it belongs to the lextensive models, such that this family kind of jointly represents the left adjoint of F, in the sense that if you have any other lextensive model, a map from F to G factors through a unique index, so factors some uniquely from some of these maps as a map of Fi into G, right? This is the left multi-adjoint. This is what it means for this embedding to be a left multi-adjoint. And from this equivalence, actually, we can build this left multi-adjoint, so this family of maps quite explicitly as follows. What I claim is that the index set, so this I here, is exactly given by points of the profinite set, so pi f. And the family of models are taken by looking at all the stalks of the profinite set. So for each point x, you have a stock functor that takes the stock of a sheaf, and the stock functor is co-continuous and left exact. So in particular, if you compose f hat with x star with the stock, you get, again, a lextensive model. And there's a canonical map from f, which is given by the left composite, as before, into the stock, because there's a canonical functor from the global section functor into the stock functor, right? So this gives you a family of maps into the lextensive categories, lextensive models. And this is exactly the multi-reflection of the left exact functor f. And you can prove this quite easily from this equivalence. Okay, so this equivalence is kind of a generalization of the spectrum construction. Very nice. Just to mention this, but okay, here's the kind of main point of proving this equivalence, is to actually notice this kind of magical result, which is that this pi functor from the profinite set, from the pro-completion of C into profinite set, is actually a Grothendieck fibration. So this is due to the fact that this is a Grothendieck fibration and you have an equivalence. But if you try to directly prove that the pro-completion of C over profinite set is a fibration, like you won't go any far. But this equivalence gives us this. And I steal the following theorem, or the following proof strategy, from a recent work by Van Dobben, Dobben, working on algebraic geometry, actually, on this exodromy theorem, that gives us the following equivalence. So let me parse this. So C, again, is a lextensive category. Category E is any category with finite products. If you want infinity category, is also fine, but okay. For today, you find a category with finite products. And because E has finite products, you have a notion of sheaves of any extensive topology over E, right? E-valued sheaves. So actually, you can prove an equivalence between the extensive sheaves of the pro-étale side, so this pro-completion of C at values E, as the following morphism between two pseudo-functors. One pseudo-functor is the pseudo-functor we have before, which is the pseudo-functor over profinite set of C sheaf-valued models, right? On the other hand, so the codomain is you take the slice, so for each profinite set, you take the slice over profinite set of S, and that is also an extensive category, and you take the extensive topology on that with E-valued sheaves. Okay, this is another pseudo-functor, and I claim there is a natural equivalence between the two. And the proof is completely formal, right? So because now C is a fibration, so you can actually write it as a coend, where the coend is indexing by the base category, and the coend basically takes each fiber together with the slice of the base category over that S. And once you write this as a coend, then the pre-sheaf category, you can take the coend out, so it becomes an end, which is the product of the opposite of these two factors. And you can take this opposite into the codomain, so this becomes the pre-sheaf category. And once you know that by construction, the opposite of the profinite thing is exactly the model thing, right? So it's exactly S-valued models. And so this gives an equivalence, and this end, by the end formula for morphism between stacks or pseudo-functors, is exactly the set of natural transformations between the pseudo-functors. And then you verify that this restricts to actually sheaves on both sides. So if you take sheaves here, you're landing sheaves here, and vice versa. And this gives you the equivalence. And from this above equivalence of this exodromy theorem, you can actually also characterize what are E-valued sheaves of C, not of this pro-completion of C anymore, of C. And this, you just turn the codomain category into not by looking at the sheaves over this big site, but over sheaves of the small site of each profinite set as a topological space. And the proof is by sort of realizing certain future colimits that interplace well on both sides. Okay, and this gives you the exodromy theorem. And let me just quickly conclude that, in particular, this way recovers Lurie's conceptual completeness proof as we characterize in particular, if, say, take E to be set, then we characterize the sheaf category over C as certain, the category of pseudo natural transformations between two stacks over profinite sets. And in fact, both of these are stacks over the profinite sets for the coherent topology. And so these two are the so-called condensed categories, and this will be the category of condensed functors, if you like, from the condensed category of models into the condensed category of set, if you want. And the same story can be used to treat the case of pre-topoe as well. And yeah, coming back to Lurie, this is the explanation that condensed functors are sort of the same thing as left ultra functors, but this already is observed by Lurie as well. But this approach is slightly more flexible. And my talk concludes here. Thanks.
Okay, thank you very much, Lingyuan. We thank the speaker silently, and now we move to question time. So if someone has question, they can just raise their hand and ask it. So as before, I do have questions. So while people look for some braveness to ask their question, maybe I can start. So maybe I have. Let me start with two easy questions. So there is a paper by Christoph Canalas. The title is "Positive Model Theory of Interpretations," where he seems to me is doing something similar to what you do in the first third of your talk. Do you know the paper, and am I wrong?
So I tried to find Christoph's paper, but I don't think I find it. But if you have, maybe you could send it to me, or I was thinking the wrong.
You mean you cannot find the document?
Yeah.
Oh, cool.
But I was trying to find his PhD thesis, but okay. I didn't find it. But if you have, maybe you could send me. Thanks.
Christoph recently has a web page, so I will just send you the web page.
Oh,
but that's okay.
So the brief answer is that to the precise detail, I don't know. But from what I can understand, because Christoph, he mainly works over Boolean valued models, where there you actually need a complete Boolean algebra instead of an arbitrary Boolean algebra. So for that, my only answer is that I don't know. Yeah. But it would nice. I was trying to find out, but yeah.
Okay. Do we have other questions from the public?
Can I ask? Can you say something about what changes when you move to pre-topoe? So like how do you need to be careful with the APIs?
Right. So if you see here, this equivalence works for every lextensive category, right? So in particular, it works for when C is a pretopos as well, because every pretopos is also lextensive. So this actually characterizes the pro-completion of a pretopos not via its models, so not via its coherent models, but via its lextensive models, right? Because on the right-hand side, we always have the lextensive functors from C into some sheaf category over a profinite set. So that's one complexity where actually on this side, we want to actually use the models of C, which are not just extensive models. So we need to restrict this category to maybe a full subcategory that will land us into actual models, not just like extensive models. But that part is done already by Lurie, right? So this equivalence generalizes a result by Lurie. Lurie only have this result for a full subcategory of this with the models on this side for pre-topos. But now this works for any extensive category. That's kind of the only complexation. And in that case, because on this side, by the construction, basically, it is always a fibration. So yeah, the same proof carries over for the exodromy theorem, except in here, actually proving that they both restrict to sheaves is slightly more complicated because you need certain descent property to hold, but that can be done. But that's the only complications in this approach for the first order case. Yes, thanks.
Okay, thanks.
So if I can, I do have another question. Towards the end of the talk, you start talking about condensed sets. But how far are you from actually just taking the topological profile and just replacing the site of topological spaces with the site of profinite sets, and in some sense cross your fingers very strong and hope for the best? Do you understand the question, or I should phrase it differently?
Yeah, I understand the question, but okay. Here I mentioned they are profinite sets, they're condensed categories or something like that, just by observation, right? I just observed that these two pseudo functors actually satisfy the descent for the coherent topology on profinite sets. But whether you take in this kind of cat-valued pre-sheaf category or the full subcategory of condensed categories, it does not matter, right? Like for this result to hold, I said nothing about the descent property over profinite sets.
No, I don't understand that, but what I'm trying to say is what you're doing some kind of representation via topological profiles, but instead of using topological spaces, you're looking at profinite sets. Is this what you're doing?
Yeah. And
Okay.
the reason is that we have a fibration here.
But then do you agree that do you think that profinite sets can really replace entirely topological spaces when we move to geometric logic or fragments of geometric logics? You don't know.
Probably no, actually. But the whole point of we're using this profinite set is exactly because of this lemma that I talked about, which is actually the only difference between a Lex functor and a lextensive functor is on their value of 2. So yeah. This is where Boolean algebra came up. This is where profinite sets came up. I would say that. Yes.
Thank you. Are there other questions from the audience? If not, then we thank the speaker one last time. Thank you, Lingyuan.